All right, so we're starting with page 128, number 15. All right, so here, this gives us a position-time relationship. Okay, but it's got a constant in it, and it says show that the acceleration is constant, and then find when the velocity is 0 and determine the position. So we're going to need all three functions here. So let me start by writing it out. So S of t is equal to kt squared. All right, plus 6k squared plus minus 10k t and plus 2k. All right, and k is a non-zero constant. All right, so here, let's take a look at what we need. So we definitely need the derivative because that's going to give us the velocity. Okay, so this is just going to be k is just a constant, so that'll be 2kt. Okay, and the derivative of t, of course, is 1. And this whole thing is just a constant. So plus 6k squared, minus 10k. And then, of course, 2k is just a constant, so the derivative is going to be equal to 0. Okay, so any questions here as to how I found the derivative? All right, so now the first question is actually about the acceleration. So the acceleration, of course, is going to be the second derivative of the position function. Okay, and so here, this whole addition and subtraction, these are all just constants. So they're just all going to disappear. The only term that remains is this one here. And again, 2k is a constant times the derivative of t, which is 1. So just 2k. Now, just to be sure here that since we're not working with x as our independent variable, t is our independent variable. When I'm writing prime and double prime, we're taking the derivative with respect to t. So it's assumed that these derivatives are with respect to whatever the independent variable is. Okay, but now we can answer part A, because part A has the second derivative, which is the acceleration, is just equal to a constant, and that's 2 times k is just a constant. It's not dependent on t. Okay. So any questions on part 1? Okay. Or part A. Now, by the way, we shouldn't have been surprised at all because the original function, despite the fact that it looks, pretty ugly, is just a quadratic function in t. And of course, we know when we take the second derivative of a quadratic, we're going to end up with just a constant. All right, so let's go to part B. In part B, I forgot what it asks, says, find the time when the velocity is 0 and determine the position. So I'm just going to take the velocity function here and set it to 0. So 2kt plus 6k squared minus 10k. And so here we're just going to solve for t. All right, so I'll bring these two things to the other side. So it'll be plus 10k minus 6k squared and divided by 2k. And here, I don't think I need to actually factor that in the numerator. I'll just do the division in my head here. Okay, so I'm going to distribute the division. So 10k divided by 2k is just 5. And then here 6 over 2 is 3. K squared over k is k. So we notice here that the time value at which the velocity is equal to 0 has that constant in it. All right. So now they want us to determine the position at this time. So I'm just going to put in for t 5 minus 3k. Okay, and this is going to be pretty messy. So I'm going to have you folks keep an eye on this. I'm going to go down here. So I've got a little more room to write it out. So k times 5 minus 3k squared, and then plus 6k squared minus 10k times the t value, which is 5 minus 3k, and then plus 2k. Okay, and this, honestly, folks, is just one big sort of distribution problem. Okay, so it looks awful, but really it's just a distribution problem. So k, so this is going to be when you square a binomial. So you can either write it out, or if you know that little trick for squaring a binomial is you square the first, okay? You square the last, okay? So 3k squared, 3k times 3k is 9k squared, and it's twice the product of first and last, okay? So 5 times 3 is 15, times 2 is 30k, okay? So if you need to actually write it out, you can do that, but there's a little trick for squaring a binomial. Okay, here I will have to distribute though. 6 times 5, so that's plus 30k squared. It's going to be 6 times 3 minus 18k cubed. Here it's negative 10 times 5, so minus 50k. And then negative 10 times negative 3 is plus 30k squared, and then plus 2k. Okay, it's quite a mess, but let's see if we can do. So let's do the cubes here. We have 9k cubed minus 18k cubed. So that's negative 9k cubed. Let's do the k squared. So here I have negative 30 plus 30, that's 0. But then plus another 30. So that's plus 30k squared. And it looks like we just have k's left. So 25 minus 50 is negative 25, plus 2 is negative 23. Okay, so quite a journey, but this is the value of the position when the at the time when the velocity is 0. Can anybody confirm this answer by any chance? No, well, we'll cross our fingers and hope that it's correct. Okay. But other than that, it would be just probably this little multiplication, just a addition error. Okay. Can I move on? I forgot who asked this one. Yeah. Okay. So let's move on to the next one. So this is not a particularly interesting question we did here. You know, it really was a bunch of algebra more than anything else. Okay. So let's take a look now. We are going to number 17 on page 129. So here we've got page 129. Actually, I guess the other one was also page 129, number 17. And let's see what this one says. It says an object moves so that its velocity is related to its position. Okay, so they give us this function. Velocity is equal to, and this is b squared 2g, and s here represents the position. Now, what type of function would this be? Because velocity, what is the usual, you know, when we're calculating velocity, it's with respect to what variable? Anybody remind me what variable velocity is with respect to? Anybody? It's about the easiest question I'm going to ask.
Time.
Yeah, it's with respect to time. Okay, but here we have the velocity, which is given in terms of position. But position, of course, is also with respect to time. So this is just an example of a composite function, because I've got velocity given in terms of position, but of course, position is a function of time. Okay, but all these other things, B and G, and they tell us in the questions, are just constants. Okay, so you know, I think we're going to have to, you know, I suspect we're going to have to take a derivative here at some point. Let's keep in mind that these are just constants. So let's see what they want us to do. It says show that the acceleration of the object is constant. So of course the acceleration, okay, which is, you know, again, also a function of time, is just the derivative of the velocity with respect to time. Okay, so let's take the thing here. So of course, I'm going to use the chain rule first time here. You know, it's just u to the 1/2. So that's going to be 1/2 u, which is b squared plus 2gs to the negative 1/2. And then I have to multiply it by the derivative of u with respect to t. b squared is just a constant. Okay, so the derivative of b squared is 0. 2g is just a constant, and it's multiplying s. And this is the trick here, is s, as we just said, which is the position, is a function of time. We just don't know its equation. So I just need to write this as s prime at t. Okay. And so now let's try to simplify this, because clearly they're telling us that this is supposed to be constant. So let's see what happens. Well, the 2 here cancels out with the 2 there. Here I have a negative exponent, so this is going to go to the denominator. So what's the only thing I'm left in the numerator is g times s prime at t. Okay, and in the denominator we have b squared plus 2gs to the 1/2 because of that negative exponent. But it's not clear yet that this is going to be a constant. But what is s prime at t equal to? Who's going to remind me what s prime at t represents? The derivative of s with respect to t. Can anybody remind me what that's equal to? What is the derivative of position with respect to time? Again, this is going to be the second easiest question I ask. Yeah, s prime at t is just equal to the velocity function. So in other words, this expression in the numerator can just be replaced by the velocity function. And I think now you're going to see what happens. The velocity function is just the square root of b squared plus 2gs. And of course, in the denominator, this just represents the square root of b squared plus 2gs. And lo and behold, those things just cancel out. And I'm just left with g, and that's a constant. Okay. Yeah, Elliot, you have a question?
Yeah, my question is specifically when the equation goes from just an s to derivative of s with respect to t.
So
How
here,
does that work?
yeah, so here, even though they just write s, we know that position is a function of time. So it's when I'm in, as part of the chain rule, I have to take the derivative of the inside function. So I have to multiply the derivative of the outside function by the derivative of the inside function. Well, the derivative of b squared is just a constant, so that's 0, plus this is 2g times the function s of t, the position. So 2g is just a constant, and now I have to take the derivative of this function. But they didn't give me the formula for the derivative of that function, so I just write it as the derivative of s with respect to t. So I got to this as part of the chain rule, taking the derivative of the inside function. Okay, does that make sense?
Yes, thank you.
Okay. Okay, and there you go. We've shown that it's a constant. So again, questions like this, what they're really testing here is they're testing, do you understand, like, with some depth, the way the chain rule works? Okay, that you have to take the derivative of this inside function. If you happen not to know the equation of the position function, you still are taking the derivative of it. Okay, so that's sort of the first piece of understanding you have to have. Then the other piece of understanding is to realize that the derivative of the position function is equal to the velocity function, which is given by that expression. That's why I'm able to replace s prime at t by this expression, because s prime at t represents exactly the velocity of the object. Okay? Any other questions? Okay, so there's some subtlety here. There's a reason why this is in, part C. The previous question, was annoying. There certainly was a lot of writing, but there was nothing too, it was just a lot of algebra. Okay, this here, you really have to have a subtle understanding of what it means to take the chain. Okay, so if there's no other questions, let's move on to the next one I have, which is page 170, number 10. So 170, number 10. Okay, which is actually on page 171. So let's take a look here. Hopefully I'll have enough room. And let's see what this question says. It says use a derivative to show that the graph of the quadratic function, okay, and again, we see that this has a bunch of unknowns in it. So here, ax squared plus bx plus c, okay, and here they're specifying that a is greater than 0, and they want us to show that it's decreasing on x less than negative b over 2a, and it's increasing on x greater than negative b over 2a. Okay. I wonder what negative b over 2a is representing. I guess we'll see in a second. But given that the a value is positive, it makes sense that this thing is decreasing and then increasing. Okay. But of course, we need to show all these things. All right. So of course, the first thing I'm going to do, since I'm talking about decreasing and increasing, is I'm going to have to find the derivative. Okay. So let's take the derivative of this function here. So again, a is just a constant times the derivative of x squared, so times 2x. So this is just going to be 2ax. And then here, the derivative of x is 1. So I'm just going to be left with b, and the derivative of a constant is 0. Okay. Now, the only places where this can change signs, since it's a polynomial, is at an x-intercept. So it's not like we have to look for where it doesn't exist. It happens to be a polynomial, so the only place we need to look is where it's equal to 0. And so here we realize that x is just going to be equal to negative b over 2a. Okay, now I want you to think about this later on. It's not specifically the question they're asking us, but I think we might have stumbled on a really quick way of determining where the vertex of a quadratic is. Okay, but for now, what we need to show is that it's decreasing to the left of this number and increasing to the right of this number, which we know is what should happen. But I guess they're asking us to try it, to show it, I mean. And so here, I'm going to do what I normally do. I'm going to create a number line. So all I need is any value to the left of this number to find the sign in this interval. And similarly, any number to the right of this number to determine whether it's positive or negative. So the problem is I don't know what this number is. But can somebody tell me what will guarantee that I am to the left of this number? What is the easiest thing I can do to guarantee that I have a number to the left of negative b over 2a? Would anybody like to suggest something to me? There you go. Take this value and just subtract 1. So I'm going to use here negative b over 2a minus 1. And then I'm not even going to bother asking, because if I want to be guaranteed that I'm above this number, why not take negative b over 2a plus 1? Okay. And so now I'm going to test the derivative at these values. So f prime for this number here, well, it's going to be 2a times, well, here's my number, negative b over 2a minus 1, and then plus b. Okay. And I'm just going to simplify. Well, look at what happens when I distribute this. The 2a's cancel out, and look what I'm left with, just negative b. Here I'm left with plus 2a. Okay, and then here I'm just left with a plus b. All right. And so what we have is we have that. What happens here? Look at that. The negative b and the b cancel out. Oh, wait. Is somebody going to spot my mistake here? Come on, folks. Why did nobody spot my mistake? Yes, come on. This is going to be minus 2a. Okay. Now, how did I spot it? Because what I'm doing is I'm doing what I tell you folks to do sometimes, is I take a look back up to my previous step to make sure that I have it correctly. So I just do it in my head. Okay. Oh, there we go. I just noticed, looked like Ed was a little faster on that one. Yeah, 2a would be negative. Good. So here, negative b plus b, and look what we're left with, negative 2a. Why is this less than 0? Can somebody tell me why I know for sure that this is less than 0? What piece of information do they give me that I know that this has to be less than 0? There you go. They tell me that a is positive. So that's less than 0 since a is positive. And then similarly, I'm going to do the same thing here. So it's negative on this side, so decreasing. And then here I'm going to do the same thing. F prime is 2a times negative b over 2a plus 1. Okay. And when I distribute, this time I will try not to make a mistake. I'm going to be left with 2a's cancel out. So negative b plus 2a plus b. And look what happens. This is positive since a is positive. Okay. And there you go. I've just proved now that it's decreasing to the left of negative b over 2a and increasing to the right of b over 2a. Okay. But what did I do here? So again, this doesn't look exactly like something we've done before, but I've just applied the exact same principles. I found the derivative. I determined the only place the derivative could change sign, and I used some number to the left of that number, to the right of that number, and tested the sign of the derivative. Where I needed to be a little clever is to say, well, I need something that I am guaranteed to be smaller, okay? And it turns out that by subtracting 1, it's smaller. By adding 1, it's going to be bigger. Okay? Any questions on this one here? Okay, so it's good. We are asking the interesting questions. That is good. All right, so let's move on to the next one, page 170, number 14. Oh yeah, that's the one that a few people asked about. Now, I'm going to guess maybe people did not watch the video on number 13 because there's a very similar problem, okay, that I did. Okay, so let's see what they're asking for. It says, let f and g be continuous and differentiable functions. So by the way, the only thing that what that tells us is that we don't have to worry about anything funny going on. These are nice functions. We don't have to worry about the derivative not existing in these intervals. Okay, so they're both increasing, and f and g are both negative on the interval. So let's maybe write down that information. So f is increasing on the interval, g is increasing, but f is less than 0 and g is also less than 0 on this interval. Okay, so this is the information that I'm given, and what they want to know is f times g increasing, decreasing, or neither. Okay, and I think when they say neither, I think they mean that it might alternate. Okay, not that it's never increasing or never decreasing, but likely that you can't say that's the same behavior. But I guess we'll see. Who knows? Okay. So with a question like this, where you don't even have any equations for these functions at all, again, the point of this question is, do you really understand what it means to figure out the increasing or decreasing nature of a function? Okay, so what is it that I need to determine in order to figure out whether a function is increasing or decreasing? So who wants to remind me, what's the only thing I really should be focusing on here? So I want to determine whether this function, f times g, is increasing or decreasing. What am I trying to determine? Yeah, but what about the rate of change? We're not being specific enough. What is it about the rate of change that's going to help me determine? Exactly, it's the sign of the rate of change. Okay, that's what this is all about. The only thing I care about is the sign of the derivative of this function. If it's always positive, means it's increasing. If it's always negative, it's always decreasing. And if we can't say that it's always positive or negative, then I guess we'll go with neither. But in the end, that's the crux of this problem, is finding the sign of the derivative. Okay. Now, without equations, we have to hope we can make some sort of determination on that. But I guess we won't know until we start by finding the derivative. So step one is to find the derivative. So let's take FG. Let's take the derivative of FG. And what do we have? Well, I have to use the product rule. I have F prime times G plus F times G prime. Okay. Now, like I said, they don't give us the equations for any of these things, but what do they tell us about this function that is related to F prime? They tell me that F is increasing on this interval. So I know that F prime is going to be positive. Okay. What else do they tell me? They tell me that on this interval, G is negative. So let's say Y here. Okay, so here, since F is increasing. So that's kind of the first one. What else do they tell me? They tell me that G of X is negative on this interval. So I know that whatever X value I'm talking about on this interval, they tell me that G of X is negative everywhere there. Okay, let's keep going. They also tell me that F is negative. And they tell me that G is increasing. So that means G prime must be positive. Okay. So while I don't know any exact value, I do know the sign of each of these components of the derivative of F times G. But of course, now a positive number times a negative number is definitely a negative number. And I'm adding to that another negative number. Okay. And what happens when I have a negative number and I add another negative number? Well, the result is going to be negative. Okay. I don't know if it's going to be negative 13 or negative 23 or negative 7.5. I don't care. The only thing I know for sure is that if I start with a negative number and I add to that another negative number, so negative 17 plus negative 23, I know I'm going to end up with a negative number. And so what this tells me is that on the interval AB, FG prime is less than 0. Therefore, what can we say about FG? It's decreasing on AB. Okay. And I was able to make this determination working only with this information given to me, but this information all involved the signs of the individual components. Okay. And that's it. That's all we have to do on that one. Okay, any questions on this? No? Okay. So let's move on to the next one, which was 178, 5D. 178, 5D. So it's actually on 179. All right, so what does it say? It says determine the critical points for each, determine whether the critical point is a local maximum or minimum, whether or not the tangent is parallel to the horizontal axis, I guess is what it means. The tangent is has a slope of 0. Okay, so I gave you D, so that is x squared minus 1 to the 1/3. Okay, so here f at x equals x squared minus 1 to the 1/3. Okay, and here they're asking us to find the critical points and to see if any of them are max or minimum. So here I'm just going to follow my my algorithm for determining local extrema. Okay, so step one is to find the derivative. So this is going to be 1/3 x squared minus 1 to the negative 2/3 times the derivative of x squared minus 1, which is 2x. Okay, and let's clean this up. And of course, we want to determine where this is equal to 0 or does not exist. These are the two things of interest. Because by the way, if you look at this function here, I notice that despite the fact that I have the exponent 1/3, this function is defined everywhere. Okay, the domain of f is all real numbers. There's no x value that I cannot put into this expression because, of course, cube root doesn't have the restriction that the inputs have to be positive. Okay, cube root can take both positive and negative values. Okay, so I'm going to clean this up before we do any work. So 2x, the 3 will be in the denominator, and here this is going to be x squared minus 1 to the 2/3. Okay, so f prime at x is equal to 0 if x is equal to 0, and f prime at x does not exist. Well, if the denominator is equal to 0, so I'm not going to bother factoring this because it's pretty straightforward. So here x is -1 or 1. Okay, so that means these are my critical numbers. Okay, and since the y values all exist for these are all going to be critical points. Okay, they're all possible extrema. Okay, so let me make my little chart here, 0, -1, and 1. And so here, let's pick some number, let's say -2. And this actually ends up being a lot easier than it looks, because if you look at the denominator, you look at this exponent, and part of the exponent is that I'm squaring it. Because remember what 2/3 means. It means you're squaring it and then taking the cube root. So the denominator is always positive. So I only need to look at the numerator. So it's negative over positive. So it's negative there. Same thing here. If I take -0.5, the numerator is going to be negative. Denominator always positive. Okay, here if I take 0.5, the numerator now is positive and the denominator is always positive. Okay, and the here if I take 2, the numerator is positive, the denominator is always positive. So there we go. So now we see that we have only one local extremum. So at 0, the derivative goes from negative to positive, meaning the function goes from decreasing to increasing. So I must have a local minimum at 0. Okay. And not only do I have a local minimum, here the slope of the tangent is 0. Okay, so I forgot how they asked it here. The odd way of asking for it says the tangent is parallel to the x-axis, which of course, being parallel to the x-axis means you're just horizontal. You have a slope of 0. Okay, now I do not have local extrema at -1 and 1 because the sign doesn't change. Okay, and when I look at the derivative, I see that the derivative doesn't exist at those points. Okay, so here at x equals 1, -1, oops, we have the negative, tangent is not parallel to x-axis because I see that the derivative is not equal to 0. The derivative doesn't exist. By the way, what is likely happening here? If the function exists at 1 and -1, but the derivative doesn't exist at 1 and -1, what is likely happening? Can anybody remember what we've seen in the past that could produce such a scenario? A waterfall? Maybe if we could be a little more, possibly a cusp. Okay. But what can you tell me about the tangent? If the derivative doesn't exist, but the point exists there, Yes, so what type of tangent is that? So Critch is saying it's approaching infinity. So what type of tangent would that be? There you go. Very likely the tangent would be vertical here. Okay, so of course, best thing to do is just take this, stick it into Desmos, and confirm if that's the case. Okay, but we know for sure there's no local maximum minimum there because the sign doesn't change. All right. Any questions on this here?
So, just a question.
Yeah.
If it doesn't exist on the derivative, does that mean we can assume that the tangent is not zero there and therefore not horizontal to the axis?
Yeah, because the only way for the tangent to be horizontal to the x-axis is if it's a horizontal line. So the slope would have to be 0. Clearly, the derivative is not equal to 0 when x is equal to 1 or minus 1. The derivative does not exist there. So definitely can't be can't be parallel to the x-axis. Okay.
All right, thanks, Tony.
Yeah, Samantha.
Wait, so at the local minimum, it's parallel to the x-axis?
Yes, because at 0, where we have this local minimum, the derivative is equal to 0. And of course, what does the derivative being 0 mean? It means that the slope of the tangent is 0, hence it's a horizontal line.
Okay, I get it.
Yeah.
Thank you.
Yeah, see again, this is where try not to get thrown off by the funny language that they're using. You know, they're saying, oh, when is the tangent horizontal to the parallel to the x-axis? It's just another way of saying, when is the slope of tangent 0? Okay, or when is the tangent a horizontal line? They're just kind of saying it in a bit of a funny way. Okay. So I'm just gonna, since there's time, I'm gonna go back up because there were some other questions people had put in. So we had lesson 1, homework number 4. And then here, could you go over question 4 from unit 3, lesson 1? Oh, that's the same one. Page 121, sorry, 128, 10E and 17. Okay, so I already did 17, so maybe you came in a little late, so you can go back and check that one. And 10E. Okay, so let me let me do this 10E first, and then we can take a look at what is it? Lesson 4. No, lesson 1, homework number 4. Okay. So here, page 128, number 10E. Okay, so here they give you a function, position function. So let me just write that down here. We got our position function, which is t to the 5/2 times 7 minus t. Okay, and that's for t greater than or equal to 0, not surprisingly. Okay, and then in E, it says, when does the object return to its original position? So there's a whole bunch of other questions. So I'm not going to bother looking at those other questions. But here, you have to think that this is an object moving along a straight line. Okay, it could be moving back and forth. Who knows? Okay, so where does this object start? Who's going to tell me where this object actually starts at t equals 0? And again, I think this replaces the second easiest question I'm going to ask. Who can tell me where this object starts? Come on, just stick t equals 0. Yeah, at 0, because when I stick in t equals 0 here, this whole thing becomes 0, and then the whole product becomes 0. So this starts at the, what are they calling it here? They're calling it the, at 0, which is the original position. So essentially, this is asking, when is it returning to 0? Okay, so in other words, I need to solve when this thing is equal to 0. So t to the 5/2, sorry, times 7 minus t. And this is equal to 0 when t is equal to 0, okay, which we already know, that's the starting position. And the next time it's equal to 0 is at 7. So this must be when it returns to its original position, because it can't be equal to 0 at any other value between these two. Okay. Now, who knows what it does between, t equals 0 and t equals 7. It could be going in this direction back and forth, but eventually it'll come back, or maybe it's going in that direction. Like that's maybe what those other questions involve. But here, the only thing we care about is when it returns to its original position, which is 0, and that must occur at t equals 7. Okay. So here, returns at t equals 7. Okay, since there are no other values where s at t is equal to 0. Okay, and we know that because it happens to already be in factored form. Okay, and we see that these are the only two times that the object is at the origin, right at the beginning, and then the next available time would be at 7. And of course, here I should probably put, I'm assuming this is in seconds. Yeah, that's 7 seconds. Okay, does that answer the question?
Yeah, thank you.
Okay, perfect. And the next one was, so this one I'm going to have to look for. Just give me a second. So this is going to be okay, so lesson 1 homework. Okay, and this is number 4. So this is sketching one of the graphs. Okay, so I'm not going to bother printing it out. I'm just gonna eyeball it here, draw another version of this. Okay, so this is unit 3, lesson 1 homework, number 4. Okay, so let me draw a version of this. Okay, so let's see what this looks like. Looks like this. Down, up. There we go. Okay, so more or less this is what it looks like. Okay, and so the first thing I want to do, since I'm going from the derivative and I want to draw the original function, okay, and I'll just draw one version, and the other one, of course, we know would just be some sort of vertical shift, okay, but I'm going to focus on where the derivative is equal to 0, because I suspect that where the derivative is equal to 0, I'm going to have possibly a local extrema. Now that we know a little more about these, we actually know for sure there's going to be a local extremum there, because we see that the derivative is going from positive to negative, and here the derivative is going from negative to positive. So there's a sign change. So we would have done that by just reasoning it out. Now we've kind of shown that that's what has to happen in order for there to be a local extremum. Now, of course, what I don't know, what the derivative doesn't give me any information about, is the value of the function. So I'm just going to pick some generic value here. There you go. Let's say this is the y value. Okay, and I know that it's going from positive to negative, so it must be going from increasing to decreasing. So there must be a local max at this value here. Okay, and then similarly here, it's going from negative to positive, so it's going from decreasing to increasing, so there's going to be a local min at this x value. Okay, but for now, let me just see what's happening to the left here. Okay, so I see that the derivative is always positive. Okay, so it's always going to be increasing as I move from left to right. But I notice that as I go to negative infinity, my function, or sorry, my derivative is getting closer and closer to 0. So that means the slopes of my tangents are going to be getting flatter and flatter and flatter. Okay. But since they have to be getting flatter and flatter and flatter, it's clearly this is not going to go down to negative infinity, because that would mean that it'd be getting bigger and bigger and bigger. So likely somewhere here, and it could happen below the x-axis, above, but somewhere here, there's likely going to be a horizontal tangent. Okay, so at some point here, you see they're getting more and more positive, so they're getting steeper, 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 and then somewhere here, they start getting less and less positive, so the slopes are going to get less and less steep until they start approaching 0. So my function probably looks something like that. Okay, so at some value here, wherever the maximum is, it goes from getting the derivative bigger, so steeper, to starting to get less steep. Okay, here again, we don't know what the y value is, but at some point I'm going to have a minimum. So this function here is going to get to its maximum steepness around there, and then it's going to start getting less steep till it becomes 0. And then to the right, it's going to be increasing because the derivative is positive, but the derivative is also getting bigger and bigger and bigger. So the slopes of the tangents, okay, the slopes of the tangents must be getting steeper and steeper and steeper. So my function looks something in the neighborhood of this here. Okay, so in some ways has some, similarities in terms of shapes, but where's the maximum minimum occurring? Where the derivative has its x-intercepts. Okay. So for whomever asked this, does that kind of give you a sense of the process that I go through when I'm figuring this out? Okay. The idea is, you see that conversation that I talked out loud, like that's the conversation I'd be having in my head if I was doing it on my own. Okay. And that I suggest you have is talk it out as you're looking at the derivative, describe what the derivative is doing, and then make the connection to how the function has to behave. All right, Samantha?
So what would another option look like? Would it be like a shift up
Yeah.
or something?
So draw any function that is a shift upwards, downwards, and, do your best to make them look, sometimes what I would do is I'd put a little dotted line to make sure that these sort of special things happen, at more or less the same places. So what would it look like? It would look something like this. And then here it would start flattening out somewhere around there. And then here your maximum steepness would occur somewhere there. Okay, maximum steepness, then starts getting less and less steep. There you go. And then go up. And something like that. As long as it looks reasonable, I'm happy. It doesn't have to be perfect. But let's say you were to draw this like this way. It still has the behavior of getting steeper and steeper and steeper, but clearly these two functions look like they have the same slope of tangent at every x value, whereas if I drew it something like that, clearly they wouldn't have. So as long as it looks reasonable. Okay. Any other questions we want to ask, even if just from a conceptual perspective? No? Okay. So just, to repeat, most of the questions you folks were asking me here were the most interesting, the most difficult questions that there were, because they relied on kind of really understanding the concept and how to be able to apply it in a less familiar circumstance. Okay, so we always remember that we want to make sure we know how to do the more straightforward stuff. That's going to be the bulk of your evaluation, but these are the types of things that could show up in the thinking section. Certainly most of the questions that we asked today, they would be in the thinking realm. Okay, so if there's no other questions, I'm gonna stop the recording.